Hi everyone, I'm Nils Asmussen and this is joint work with my colleagues from the Barkhausen Institute in Dresden, Germany. And it's about efficient and scalable core multiplexing with M³v. Our work is based on the M3 system architecture, which is a hardware operating system co-design that integrates different cores and accelerators into the same system. Most importantly, it introduces a new hardware component called data transfer unit, DTU, into every tile of this tiled hardware architecture. The DTU both isolates tiles and also allows communication between tiles. The operating system is running on a dedicated tile and is responsible for setting up these communication channels between DTUs and between the applications running on the remaining tiles here. The communication is a fast path communication in the sense that after setting up such a channel, the operating system is no longer involved in the communication. One of the benefits of this architecture is that we can better integrate accelerators into the system. As we have shown before, we can, for example, do what we can see on the slide here, that we integrate hardware accelerators for image processing into such a shell command and pipeline them and connect them with other programs and also with the file system. However, core multiplexing is challenging in this architecture, and this is why the original prototype M3 omitted it altogether. That means an application is running on a core or an accelerator alone and is running until its completion. And this, of course, prevents us from fully utilizing the cores and accelerators in the system. In our follow-up work M3X, we addressed this challenge and added a multiplexer into the operating system that multiplexes the cores and accelerators remotely from the OS tile and with the same mechanism for both accelerators and cores. However, it revealed significant performance problems for context-switch heavy workloads. And this is why in this work we show a new approach to multiplex general purpose cores by adding a core local multiplexer into every tile, the so-called tile mux, that is multiplexing this tile among multiple applications. And most importantly, we virtualize the DTU to make that efficient and secure. You might be wondering now, why is core multiplexing actually hard? Don't we already know how to do that? Well, the problem is that core multiplexing conflicts with fast path communication as we have that here in the system. And let me illustrate that with an example. So let's say we have three applications, application 1, application 2, and application 3, and we have a communication channel between application 1 and application 3. At some point, application 1 might be waiting for the next message from application 3, and of course, we want then to switch to application 2 and suspend application 1 until this message actually arrived. Then later, if the message arrived, we want to switch back to application 1 and resume it. In both of these actions, the operating system is the one that is responsible for performing these actions to do the multiplexing. And this is, of course, in conflict with the fast path communication, which has the goal to avoid the communication and avoid the operating system during communication. Therefore, there has to be some compromise between these two. And it's actually a bit more challenging because we also want to retain the strong isolation between tiles that has been enabled by M3. That means tiles should be isolated by default, and only the operating system tile should be able to give other tiles access to tile external resources, like establish message passing channels between tiles or give them access to memory. And this, for example, allows us to integrate untrusted components like accelerators or cores into the system and controlling their access to external resources. In M3, this was rather easy because there was just one application per core, but if we now want to run multiple applications per core, it gets a bit more complicated. At first, you might think that this tile mux, this tile local multiplexer, could just save and restore the state of the DTU, like it saves and restores the state of the core, in order to multiplex that among the applications. However, the problem here is that being able to restore DTU state also allows one to establish arbitrary communication channels. And this, of course, breaks then strong isolation between tiles because suddenly every tile can just decide what resources it can access. And therefore, the requirement here is that tile mux must not be able to restore DTU state. Therefore, we decided to instead virtualize the DTU to share it securely and efficiently between multiple applications. In general, in terms of isolation, you can say that all the M3 prototypes provide better isolation than conventional architectures because we isolate tiles by default, and also tiles do not share any hardware resources like caches or branch target buffers with each other. Both M3X and M3 trade a bit of this isolation for better resource utilization because they allow to share a tile among multiple applications. And you can, of course, argue that since they are now sharing these hardware resources, they are weaker isolated than if they would not share these resources by running on separate tiles. In M³v, this current work, we trade a bit more of the isolation for better efficiency by also running the tilemux demultiplexer on the same tile as the applications, in contrast to M³x, where this was part of the operating system on the OS tile. Okay, so now let us look at the virtualization of the DTU. The most important resource in the DTU are the endpoints, and these endpoints represent communication channels between DTUs. As I said before, only the operating system tile can establish these communication channels, and therefore there is a dedicated interface, the so-called external interface in the DTU, that allows to configure such communication channels. That means the operating system can configure these endpoints to different types of endpoints at runtime. For example, a send endpoint to send messages to others, or a receive endpoint to receive such messages from others. To use these endpoints, there's another interface called unprivileged interface that is usable by the applications. And this interface, of course, can just use these endpoints but cannot change them or cannot add new endpoints. As I said, we now want to support multiple applications that access the same DTU. And therefore, we added another interface, the so-called privileged interface, that can only be used by tilemux, so by the component that multiplexes this tile among multiple applications. And as you can imagine, the first thing that we need to do is we need to make sure that each application can only use its own endpoints and not the endpoints of other applications. And therefore, we tagged these endpoints with the ID of the corresponding owner, and also we store the ID of the currently running application in the privileged interface, so accessible by tilemux. And with this, we virtualize the DTU because now multiple applications can access the same DTU, and the DTU keeps state of multiple applications at the same time and gives them direct access to that and makes sure that it's secure. And of course, we need to solve other problems for that as well, and we want to look at a few of them in this talk. So the first one, as I said before, is that we want to be able to block applications. So if the current application is waiting for new messages, we want to give other applications the chance to run. I also said that we want to use fast path communication. That means we want to not involve other components in the communication, like the operating system tile or tilemux. And therefore, by default, applications directly interact with the DTU and fetch messages from the DTU. And only if there is no message left and at the same time other applications are ready to run, then tilemux is involved. That means the application is notifying tilemux that it wants to block, and tilemux can do the corresponding action. However, it's actually not that simple because there's a race condition. We cannot just first check for new messages, and if there are none, block the applications. Because this is similar to the lost wake-up problem, where we might receive new messages in the meantime and then lose these message notifications. We solved this race condition by not just storing which application is currently running, but also tracking the number of new messages for the currently running application. And therefore, the DTU tracks them by incrementing and decrementing the counter correspondingly. Additionally, we offer a command in the privileged interface that allows to atomically switch to a new application, which can be used by tilemux to prevent that message notifications are lost. The counterpart of blocking is unblocking, and therefore let me first start here with the problem in M³x that we had. So in M³x, the problem is that incoming messages cannot be stored in memory in the receive buffer if the receiver is currently blocked, so not running. And the reason for that is only the endpoints of the currently running applications are known to the DTU. And therefore, if the receiver is not running, the DTU simply doesn't know where to store the message because the endpoint is not available. And for that reason, M³x needed to resort to a so-called slow path, which forwards these messages over the operating system tile to the receiver by first scheduling the receiver and then delivering the message. In contrast to that, M³v has a virtualized DTU, which knows all endpoints of all applications on the same tile and can therefore always store the message because it knows the address where to store it. But of course, we need to do more than that. We also need to notify tilemux in case a message is received for a receiver that is currently not running. And therefore, the vDTU is injecting an interrupt in this case that can then be handled by tilemux by marking the receiver as ready or by directly switching to the receiver. I also want to highlight here again that in the best case, neither the operating system tile nor tilemux is involved in the communication. That means the operating system tile is only involved to set up or tear down communication channels, and tilemux is only involved in exceptional cases. And this also shows in the performance. So let us directly look at the comparison between M³x and M³v. So we did a performance and scalability comparison to M3X, and we used the setup that is supported by M3X as well, which means we used the M³v simulator and have 3 GHz out-of-order x86 core in every tile. On every tile, we run both the benchmark, which is either an SQLite or a find benchmark, and we run in a memory file system, which is a microkernel-style operating system service. And therefore, we have lots of context switches between these two components in order to give the benchmark access to files. You can see the plot here, which on the x-axis shows the number of tiles in order to show the scalability. And then on each tile, we have these two components that I just described. On the y-axis, you can see the overall throughput in terms of runs per second, so the number of runs of this benchmark that we can do per second. And let me start with the numbers for M3X. So you can see here that the scalability of M3X is rather poor here, and the reason for that is that there is a single operating system tile that is responsible for all context switches on all other tiles in the system, and this, as you might imagine, doesn't scale that well. You can also see that there are a few numbers missing, which is because of stability problems of M3X with higher numbers of tiles. In contrast to that, M3v shows almost linear scalability for this workload here for both of these benchmarks that we have. And the reason for that is that we now have a core local multiplexer that doesn't involve other components to multiplex. We can also compare the performance of these two by zooming into the numbers for a single tile here. And if I do that, you can see that the difference is about a factor of 2 between M3X and M3v, which stems from the fact that the remote context switches on M3X from the OS tile to the actual core or accelerator where the context switch happens is much more expensive than the local context switches in M3v. In contrast to previous prototypes of M3, we, for the first time, built a hardware implementation as well. And you can see the FPGA here that we used. And this is the hardware platform that we put on this FPGA. You can see at first we have a couple of RISC-V tiles here that each have a RISC-V core and also a virtualized DTU. Second of all, we have 2 memory tiles here that give us access to external DRAM. Then we have a debugging interface that allows us to first load programs onto the other tiles here and also to debug them at runtime. And finally, we have one special RISC-V tile here that has a NIC attached that allows us to do more complex workloads in the benchmarks that involve networking. Finally, a few more words to the RISC-V cores here. We have the option to either have an in-order Rocket core or an out-of-order Boom core. The Rocket core is clocked at 100 MHz and the Boom core is clocked at 80 MHz, which was required to meet the timing constraints of the FPGA. In both cases, they have 2 × 16 kilobytes L1 cache and 512 kilobytes L2 cache, and the virtualized DTU contains 128 endpoints. So let us start with the analysis of the size and complexity of the DTU, because this hasn't been done before. And you can see here the resource usage of the FPGA, and we can compare the numbers for different components here. So let me start with a comparison between the DTU and the Boom core, and you can see in terms of logic, so lookup tables here, there is it's about 10% of the Boom core that the DTU makes up. Even more importantly, you can see that the Boom core has much more memory usage than the DTU because the Boom core has this 512 kilobyte L2 cache. You can also see the cost of the virtualization of the DTU here by comparing the cost of the privileged interface that we needed to add for that with the overall size of the DTU, which shows that we have about 6% more logic in the DTU to allow that. And also we have no additional memory for that. Now let us look finally at the performance comparison with Linux that we did. So we run both the Linux and M³v on our FPGA platform. And we used LevelDB as the benchmark that runs on the FPGA platform and receives requests from a remote machine and sends the results back afterwards. The requests are generated with the Yahoo Cloud Serving benchmark YCSB, and we use different shares of read, insert, update, and scan operations because they behave a bit differently. In both cases, so both M3v and Linux, we use a single Boom core for the measurements. For Linux, this is required because tiles are not cache coherent, and this is why Linux can just use a single tile with a single Boom core. For M3v, we make sure that all of these components that are involved are running on a single Boom core here. At first, the components are LevelDB, which is not just having the key value store, but also handling the requests from the remote machine. Then we have in M³v a pager that is responsible for page fault handling. We have a file system, the in-memory file system as before, and we have a networking stack. And the last three components here are, again, microkernel-style operating system services that run in their own address space. And this is why, again, we have lots of context switches between these components here. In the case of Linux, of course, the three last components are part of the Linux kernel. If we look at the plot here, we can see that at first on the x-axis, there are the two different systems, M³v and Linux, and we have the different workloads that we have with read, insert, update, and scan, and also a mixed workload of these. If we look at the results, we can see that most of the time they are on the same level, but this is not the case for scan. And scan is a bit different here because scan is very memory intensive, and we believe that the reason for this difference is that the L1 cache is rather small here with 16 kilobytes only, and Linux has a much larger cache footprint than M³v, which explains these differences here. But overall, you can see that we have competitive performance to Linux despite these lots of context switches that are happening on M³v. In conclusion, M3 in general explores a new system architecture with a new pair-tile hardware component, the DTU, the data transfer unit. In this work, M3v, we show how general-purpose cores can be multiplexed efficiently by trading a bit of the isolation from M3X for more efficiency and scalability. We also, for the first time, have a hardware implementation that demonstrates that the additional costs for the DTU are modest. And we show that we now have competitive performance to Linux with context switch heavy workloads as well. The complete hardware-software stack is available as open source, so if you want to take a look or build something on top of that, please go ahead. And with this, thanks for your attention, and I'm happy to take your questions.